everybody. Welcome to chapter 6, part 1. We're going to be going through sections 6.1 to 6.4, and I will be summarizing in notes some of the key points from this chapter. I encourage you to read it yourself, look at the bold vocab words, read the different figures, make sure you're understanding all the terminology, key concepts, and you're following along well with my notes. I am going to be working an example problem right after this lecture, so make sure that you watch the video for example problem 6-1 immediately following this video. It goes well with applying some of these concepts in the notes to a problem. All right, so chapter 6, we're going to be finally looking at entropy. I know you guys have been waiting with bated breath until we can start incorporating some of that beautiful S value, and today's the day. So we're going to be getting into the second law of thermodynamics. You should remember that this states that energy has quality, and we always flow from high quality to low quality. So if you are using a turbine to heat up water, you can't then always recapture all the energy from that heated up water to use their turbine. Energy only flows one way, and obviously this chapter then also deals a lot with efficiency, performance scenarios, and a lot of different concepts about processes and reversibility of processes. All right, so let's start with the note taking. We're gonna start with the introduction and then some thermal energy reservoirs. This is on page 276, chapter 6. So I'm gonna start with the notes here. See if we can zoom in a little bit. That might be too much. Here. So we're under week 11 in the modules, week 11. This is chapter 6, and this is the second law of thermodynamics. As I said, these will be the notes summarizing sections 6.1 to 6.4. There's also a PowerPoint under this module. There's also a PowerPoint. And then example problem 6.1 as a second lecture. And please read this on your own as well. All right, so we are on page 276 for chapter 6. And this is dealing with the second law of thermodynamics. I'm going to write the second law of thermo. And the second law of thermo we went over the first week of class, but a lot of times, all the time, it will include entropy. Includes entropy. So the desire to always go towards disorder, to always go towards chaos. This is the rule of entropy, which we call S. The second law of thermodynamics is involved with the direction of processes, the quality of energy. Beefy, I'm going to need you to be a little more quiet, please. Thank you. It's associated, the second law is associated with theoretical limits. Theoretical limits, and it defines perfection for thermodynamic processes. So ideal situations defines perfection for thermal processes. Okay, so the second law of thermodynamics includes entropy, includes direction of process, quality of energy. It's associated with theoretical limits, which is directly related to perfection. We're going to look at some systems that involve the second law of thermodynamics. And these start on page 278. Page 278. And the first of these is going to be a heat engine. So heat engines here, heat engines. And before we start there's a nice little figure here that says work can always be converted to heat directly and completely, but the reverse is not true. That is the second law of thermodynamics. So we can convert work to heat, but when we add heat to water, we don't always get work. That's not the direction that energy is going to flow. That's the second law of thermodynamics. All right, getting into heat engines. You're all probably familiar with heat engines, even if you don't know it necessarily. So these are devices that convert heat into work. So an example of this that we'll talk about a little more in depth would be steam power plants. So a lot of people are currently getting their electricity from steam power plants, and these are using the heat and producing steam to create work and produce electricity. So heat engines, devices that convert heat to work, Ooh, I'm running out of room. All right. For rules about heat engines, typically they receive heat from high temperature sources, such as a furnace. Receive heat from high temp sources. So examples would be solar panel, solar energy, oil furnaces, or nuclear reactors. Rule 2 is they convert part of this heat to work. So they always receive heat from high temperature sources, then they convert part of heat to work. Convert part of this heat to work. So this generally includes shaft work. So we talked about shaft work in chapter 2, but a rotating shaft creates shaft work. There's a lot of examples of this in the book, including the one that I showed you early on here. So a rotating shaft for shaft work. For number 3, they reject the remaining waste heat to a low temperature sink. So they convert part of the heat to work and they reject the remaining waste heat. So they reject remaining waste heat to a low temperature sink. An example of a low temperature sink would be the atmosphere or a river. So in North Fort Myers, we have a park called Manatee Park, where the thermal heated water from the electricity plant is discharged into the river there, and the manatees love it in the winter. They come there when it gets a little colder in the air, and they like to swim in the warm water. So when you go there in the winter, on a cold day, you can see a ton of manatees. And it's because the power plant is using the river as this low temperature sink to waste their excess heat. All right, number 4, this is actually, I think, probably the most important rule. They operate on a cycle. Everything is cyclical. They operate on a cycle. And 5th, they involve a fluid for heat transfer. this is the last one. They involve a fluid for heat transfer. And this is called a working fluid. We've actually been working with one of these fluids for the past several chapters. An example would be R134A, which is a refrigerant. It's a fluid that is commonly used for heat transfer systems. All right. So I'm gonna put these notes over here. So an example of a heat engine as I mentioned, would be a steam power plant. And a steam power plant is an example of an external combustion engine. It's not important that you know the exact terminology of all the different combustion engines, but that's just there as a reference. All right, so on page 279 in the book, there's a nice schematic on figure 610 of the steam power plant. And I think it does a nice job of illustrating a lot of the key points for this concept, so I'm going to try to briefly sketch it after I show you what it looks like in the book. So here in the book, we can see figure 610. We have a high temperature energy source coming in, such as from solar panels or a furnace or any type of strong heat source. It's going to this boiler. We can see positive heat coming in here. And then this boiler is heating up the turbine, which is where shaft work will be occurring, and we're getting work out of this. And we have some of the cooler fluid coming into the condenser and releasing into an energy sink such as the atmosphere or the river in Manatee Park. So this is a heat coming out of the system. This cooled off water, which is now blue here because it's cool, comes into this pump. So we have to put work into this pump. If you've ever worked with a pump before, you know you have to plug it in and pump it up. So we have to put in some work here to pump back this cool water to the boiler to be heated up and sent back to the turbine. And this whole cycle continues. So for a heat engine, we have a boiler heating up the water, sending it to a turbine, which is getting the work out of this heated up water, sending it to a condenser to cool back down the water and release the waste heat to an energy sink. And then we have a pump to circulate the water back into the cyclical system, back into the boiler. So for the boiler, this is where we have to supply heat in to heat up the water. Turbine is where we get work out. Condenser is where we're getting heat out to the energy sink. And pump is where we're requiring work to come in. So we have to power the pump and we have to heat the boiler to get work from the turbine and then release our heat to our energy sink. So like I said, this is figure 610, steam power plant in the chapter. This is a cyclical process. A lot of times when looking at these problems, we define this entire process as our system. So our system boundary is this whole thing. Depending on what you define your system as, you might have heat transfer equal to 0, even though we're putting heat in and getting heat out. But if this is your whole system boundary, you could still have your heat transfer overall of your whole system equal to 0. Normally in class right now, I would ask, are there any questions? We've kind of lost that luxury, so I'm trying to be as clear as possible. I hope it works all right. So moving on, With a lot of these systems, including heat engines, we're going to talk more about air conditioning and refrigeration, which are also cyclical processes that operate under the second law of thermodynamics. We are concerned with direction and theoretical limits and how we get close to perfection. So we've already looked at efficiency before. This chapter really uses efficiency a lot and has some additional modifications to efficiency that we will look at in some of the later sections. But if you guys recall, efficiency, we've looked at, and it has this weird little loopy in. And our efficiency was our desired output over required input. That's how we defined it in some of the earlier chapters, chapter 2, I believe. And this chapter also says that this can be defined as in terms of thermal energy efficiency. So if we look at our energy efficiency of thermal, which a lot of times we just write TH, this can be our net work, net, that's a T, net work output over our total heat input. We're saying the same thing. How much heat did we put in and how much work did we get out? How much heat did we put in and how much work did we get out? And we write this often, I should just move this up. We write this often as our work net out. So our overall summation of the work out over our heat put in, Q in. So W net out over Q in. And W net out, this value here, can be equal to our work out minus our work in, is our W net out. All right, there are several ways that you could then rearrange this. You could put, we will look at rearranging this later, but just keep in mind, this is another equation that we'll be manipulating and rearranging throughout this chapter. All right, so I'm gonna move this one over here. We're going to continue with our notes on the second law. And these are going to be some of the rules. So these are some of the rules associated with the second law of thermodynamics. The first one would be heat is always transferred from a higher temperature to a lower temperature and never in the reverse. So heat always transferred from higher temp to lower temp, never reverse. The second rule is that excess heat energy cannot be recycled. Excess heat energy cannot be recycled. That's why you have to go to a condenser and release your extra heat. You can't just reuse it to heat your boiler or work on getting you some advantage here. It's considered to be waste energy. All right, number 3, every heat engine must waste some energy by transferring it to a low temperature reservoir. So not only can you not reuse this waste energy, but every heat energy must waste some energy. Every heat engine must waste some energy. Every heat engine must waste some energy. And it must waste this energy by transferring it to a low temperature reservoir. By transferring it to a low temp reservoir. All right, so essentially this is saying that heat can only ever go in one direction, from higher to lower. A lot of times we'll write this as QH to QL, Q high temp to Q low temp. Excess heat energy cannot be recycled, so you have to waste excess heat energy, and that every heat engine must waste some energy. So we can't have an efficiency of 100%. You can't reuse any of the excess heat energy, and you can only ever go from higher to lower temperature. I'm going to work example problem 6.1 now in the following lecture. So please make sure that you read for yourself sections 6.1, 6.2, 6.3, section on thermal efficiency down here, more about how we can't ever reach perfection. We have to waste some energy, and then stop here at the second law of thermodynamics, Kelvin-Planck statement, up to 6.4. All right, I will continue here in the next lecture up to 6.4. So please work the example problem, do the reading, and I will see you all next time. Thanks, have a good one.